Okay, it's been an interesting couple of weeks. A lot has happened. What One of the things that I do know is that they are going to be changing the way they do the AP exams. Okay, some of you already know this. You've seen my announcement on Google Classroom. Because of that, we're going to adjust a little bit the way we do things. Um, they're not going to cover in the exam some of the things that I thought they were going to do, but there is one thing that they are going to cover that we haven't yet, and so I'm going to go through that in this lesson today. I'm going to give you a homework assignment that goes with it. There'll be two Google, or not Google Classroom, but Albert I.O. assignments, and that'll cover this section. This section is called Simple Harmonic Motion. Okay, and once we've done that, then we've covered everything for the AP exam this year, and we'll move quickly to reviewing for the exam. This section actually doesn't take too long. It shouldn't be too difficult, but want to go through that and want to get through it fairly soon so we can start that review process. I am going to be on a video conference tomorrow evening. It's Thursday evening with the College Board. Hopefully find out a little bit more details about the AP exam, at least the dates and how we're going to do that. But when I find that information out, I'll let you know. So let's go ahead and get started on simple harmonic motion. Okay, so with simple harmonic motion, what we're looking at is motion that happens periodically, that has harmonics, that happens over and over again. Okay, the perfect example is going to be with a spring, and we've already done some of that before. So let's start with a spring that's on its side. It's attached to a wall. And it's attached to a mass here with mass M. Okay. Now, we're going to ignore a few things. We're going to ignore the mass of the spring. If you want to be really accurately, we have to include that. But for right now, let's pretend the mass of the spring is so small that it's not important. Okay, well, the spring has a natural position where it normally rests, and we would call that the equilibrium position. And I'm going to mark it right here. Here's our equilibrium position. Okay, and if you remember from before when we were talking about forces and energy with springs, we said that the force is governed by Hooke's law, F equals kx, where k is something called the spring constant, and then x is the displacement. And by that, we're talking about how far it goes from this equilibrium position. Okay, so it can go various distances. So it can travel here. Let's say we pull it back to this position here. That's going to be its maximum displacement. And the maximum displacement we're going to call A. A stands for amplitude. Okay, A is the maximum displacement. And if it gets displaced that far over here, when we let it go, it's going to pull it back. It's going to go past the starting equilibrium position. It's going to go back this way. It's going to go that same distance this way, this time compressing the spring. And we get that same value here. A and A on either side. Okay? Now, we need to talk a little bit about what's happening at each of those places. Now, at the equilibrium position, it's not moving. Or, excuse me, before we pull on it, it's not moving. There's no forces acting on it, nothing changing its motion. And that's the key thing here. Nothing is changing its motion when it's at the equilibrium position. So whatever it was doing, it'll continue doing. So if it's still at the equilibrium position, it's going to just stay still. If it's moving at the equilibrium position, it's going to keep moving at that same speed. Okay, so at this point, F equals 0. And if we look at our equation, F equals kx, if our displacement is x, or is 0, we would expect our force to be 0. Well, if the force is 0, well, because F equals ma, if F is 0, the mass didn't change, that means our acceleration is 0 at that point as well. Okay, so at the equilibrium position, F equals 0, A equals 0. Now, that doesn't mean that it's not moving. It can be moving and pass through this point, and at this point, it has no acceleration. Okay, but as it starts moving farther and farther away from that equilibrium position, we're starting to get a value of x, then that means the force goes up, which means the acceleration goes up, gets larger. And that force is always pulling back towards this equilibrium position. Okay? So the maximum value of the force is going to be at our max position. Because there's where we have the maximum displacement. Okay? And the size of that force, if our maximum displacement is A, is F equals K A. Okay, again, remember A is what X is, but only at this position. It's that maximum value of X. Now, another key thing to note here, all this discussion that we're having about how this thing moves are equations of motion remember those four? We had x final equals x initial plus v times t. We had x final, and this was where the acceleration is 0. We had x final equals x initial plus v initial t plus 1/2 at squared. We called that one Bob. That was when a is not 0. Okay, we had v final equals v initial plus at, and then we had v final squared equals v initial squared plus 2a x final minus x initial. So remember, we had these equations of motion. However, when all of these equations of motion assumed one thing. They all assume not A is 0, A is a constant. In other words, whatever our value was, A doesn't change. Okay? Well, if we look at this situation, A changes here. Our force is max here, so that means our maximum acceleration is at the ends. But as we get towards 0, the x is 0, our force goes to 0, our acceleration goes to 0. So our acceleration is changing constantly. That means all of these equations are not valid for simple harmonic motion. Okay? All of these equations are not valid for simple harmonic motion. Okay? So we're going to have to look at some other things here. Okay? So let's talk about a couple of things. One of them we've already mentioned. We already mentioned before that for the energy, our potential energy for a spring is equal to 1/2 kx squared. Now I think we probably wrote this before as PE for a spring like that. The College Board, I think, usually uses capital U here. So capital U, our potential energy for a spring, is equal to 1/2 kx squared. Okay? So if we're looking at this situation here, and we're trying to find out, well, what's the maximum potential energy? Okay, if I pull this spring out this way, I get it to the maximum position, that at the amplitude. Well, then at our maximum displacement, x equals A, our potential energy at that point is equal to 1/2 k A squared. Okay, so I pull it out here, I release it. Okay, so what happens to our mass? It gets pulled towards the center. As it gets pulled towards the center, our potential energy changes to kinetic energy. Okay? And our equation for kinetic energy was equal to 1/2 mv squared. Okay? So if I want to find out what the velocity is when it reaches this point, I can find that as long as I knew how much energy we started with. Well, we started with this amount of energy. We released it at x equals 0, at our equilibrium position. All of that potential energy turned into kinetic energy. So I can say 1/2 mv squared is equal to what our potential energy was, 1/2 kx squared. And I think we did a couple of problems like this back when we were talking about energy. The 1/2s cancel out. If I want to find my velocity, divide by m, so I have v squared is equal to k over m x squared, or in this case A, because that would be our maximum position, our position we released it from. And so V, when we take the square root of both sides of this, is the square root of K over M times A squared, or if I take that A squared out, it's just A. Okay? Let's see how this looks in a quick example. Let me just put some numbers into this. Let's say that I pull this back and I pull it back 10 centimeters. Okay, so 10 centimeters is 0.10 meters. Let's say that our spring constant was 10 newtons per meter. Okay, so I pull it back 10 centimeters, I release it. So, and I want to find the velocity when it reaches our equilibrium position. Okay, 1/2 mv squared is equal to 1/2 k x squared. The 1/2s cancel out. Okay, I divide, well, I guess I need to provide some more information. I need the mass, so let me just make the mass 1/2 kilogram. Okay, so 0.50 kilograms V squared is equal to 10 newtons per meter. Our max displacement, which again is A, is 0.10 meters. Okay. 0.1 times 0.1 is 0.01 times 10 is 0.10 newtons, 0.50 kilograms, V squared, divide by 0.5. And then to find the velocity, and it's not newtons anymore, it's meter squared per second squared, because kilograms canceled out. And if I put this into the calculator, take the square root of 0.2, what I get is 0.45 meters per second. Okay, so all of this is concepts that we've learned before. It's conservation of energy. Okay, we've got Hooke's law. Okay, the only thing that's different is our equations of motion are not valid anymore. So we're going to need to be using things like conservation of energy. Okay. Some other things that we'll need to define. When we're talking about this, one back and forth motion, we're going to call a cycle. So, cycle is one back and forth motion. And it doesn't matter if we're talking about going from here all the way back here and back to the starting point here. If I go from here, there, or the equilibrium position both ways and then back to the starting position. All of those are considered one cycle.
we have something that we call a period. It's a time period. So it's a very specific time. We use capital T to indicate that, and that is the time for one cycle. We have something else that's very closely related. It's the frequency. The frequency is the number of cycles per second. So this one's seconds per cycle. The period seconds per cycle, the frequency is cycles per second, which means that the equation there that relates these is our frequency is 1 over the period, or the period is 1 over the frequency. You can use either one of those. Now, I'm going to go derive an equation here that gives us the frequency in terms of our mass and the spring constant. You don't need to necessarily remember how we got there at the end. You'll need to be able to recognize the equations, but both of the equations I'm going to give you are going to be on the equation sheet that the College Board has that you can use during the exam. Okay? So what we're going to do is I'm going to make an analogy here. So I take this spring, I pull it with the mass, I pull it back, and I let it go. And it's going back and forth. It's going its fastest near the center. It's going the slowest near the end. As it turns out, that's the exact same thing, or it looks exactly the same, as if I had something on a string, and I'm looking at it from above, and I'm swinging it around in a circle. Okay, and if I take this and look at it from the side, from this side instead of the top, then what I see is, okay, as it reaches this point, it looks like it's going the fastest. It looks like it's going slowest from right here because it's not going as far in the x distance. Okay, so it actually ends up looking the same. Okay, if I was to look at this at the side, okay, it would look like, okay, this mass that's on the string, it's going fastest here, it slows it down, it stops, or that's what it would look like, even because it's going away from me, and then it returns back this way. And as I get to here, it looks like it stops for the briefest instant. It's not really, but at this point it's coming directly towards me, so it appears like it stopped. And so if I want to relate this, what I can say is the velocity is equal to the distance around the circle. Okay, that's our circumference from geometry. If you remember, that's 2 pi r divided by the time. Our velocity divided by time is going to give us our speed. Well, if I'm comparing it to this, that farthest distance, the distance from here, is a. Okay? So then our velocity is 2 pi times the amplitude. And if I'm talking about the time it takes to go around once, well, that's the period. Okay, so it's a time, but it's that time for one complete cycle. Okay. So let's look at in terms of energy. In terms of energy for our spring, we have 1/2 k x squared is equal to 1/2 m v squared. Again, cancel out the a. We have k. Our x at the maximum distance is a. If I rearrange these, I can divide by the v squared. So I have a squared over v squared, and then divide by k is equal to m over k. So a over v is equal to the square root of m over k. Okay, so let's go back to what we had right here. Our velocity is equal to 2 pi a divided by t. If I solve for t, okay, multiply both sides by t, then divide by v, 2 pi a over v. Well, a over v, we said, was the square root of m over k. My period is equal to 2 pi square root of m over k for springs. Okay. For a spring, our period is equal to 2 pi m over k. Our frequency is 1 over t. So that's 1 over 2 pi square root of m over k, which means 1 over 2 pi square root of k over m. Sorry. All right. So I'll give you a moment to catch up since I started writing off of the screen here. Here's the way I typically remember these, and you're not going to have to memorize these equations for the exam, but the way I typically remember them is, okay, we've got a spring here with a mass attached. If my mass gets bigger, that means it has more inertia. Okay? That means it's going to take more time to change its motion, to make it go from here to one side and back the other. Okay? So m in this equation needs to go on the top. The bigger the mass is, the more inertia it has, the more time it takes for one cycle. Okay, converse is true, or the inverse is true. If I'm looking at how many per second, okay, well, my frequency, if my mass is bigger, then my frequency should go down, so the mass should be in the bottom part of this fraction. Okay. All right. So there we have springs. That's one major portion of our simple harmonic motion. The other thing
that they look at with simple harmonic motion are pendulums. Okay, everybody remember what a pendulum is? Pendulum is simply a string with some sort of mass attached, typically a ball or some sort of a bob there. I pull this back, this position, I release it. As it swings down, eventually it comes to its equilibrium position, it swings back the other way, goes up to the same height. And we talked about this when we talked about energy. Again, conservation of energy. At this point, what it has is potential energy. As gravity pulls it down, it reaches the bottom. The potential energy is gone. It's all turned into kinetic energy. It goes past this point, swings up. That kinetic energy gets turned into potential energy. Now, if we're looking at this in terms of the forces, okay, we've got a force acting on it. Okay, our force acting down is M times G. We've got a force caused by the tension on the rope. Okay, force of tension going that way. If we break that down into its component parts, and remember, this is kind of like our force or ramp forces. Okay, I'm going to rotate my point of view. Force of tension goes this way. I have a portion of my gravitational force going this way. I've got a portion of my gravitational force going this way. If I put it on the free body diagram, I should move it up there, but I'm trying to make this triangle. Okay, so this part is mg. If you remember that this part right here is mg cosine theta, and this part was mg sine theta. Okay, so my restoring force my force pulling it back towards the center caused by gravity is mg sine theta. Now, as I release it, it's got force right here. It comes down to here. It's giving up potential energy. It turns into kinetic energy. At this point right here, my force is 0. Okay, it's reached the bottom. Gravity's pulling straight down. It's equal to our force of tension. So our free body diagram right here looks like this. Our restoring force is 0. When I get over on this side, it's the same thing except in the other way. So I have mg going down. I have the force of tension going this way. Again, if I looked at my forces, if I did the same thing here, my force of tension would balance out with mg cosine theta. My restoring force would be the x component, so the mg sine theta here, that would be our restoring force. So what we can see is that it's starting to look kind of similar to what we had with a spring. We've got no force in the middle.
we've got a force when it's on this side, and we've got a force when it's on this side. Kind of like, similar to F equals kx. Okay, so our distance here, the maximum distance that we pull it, that's our x. We have our maximum force because we have the maximum angle at that point. Okay, goes to 0 at this point, and then we have the same thing on the other side. Well, here's one thing that we find. So our restoring force is the mg sine theta. At small angles, so where theta is small, sine of theta is pretty close to just theta if it's in radians. Okay? Now, this is an approximation. It's not anything that's exact. If we wanted to be exact, we want to use the sine theta. But if we want to use an approximation, we can say at small angles, sine theta is about equal to theta. By small angles, what we mean is less than 15 degrees. So less than 15 degrees